we see in front of us is the ethane molecule, which is composed of 2 carbons and 6 hydrogens. The 2 carbons are connected by a sigma bond, and because sigma bonds are cylindrically symmetrical, rotation about a carbon-carbon single bond can occur without any change in the amount of orbital overlap. The different spatial arrangements of the atom that result from the rotation about a single bond are called conformations. There are 2 extreme conformations. One is called staggered and the other one is called eclipse. What you see on the left side is the staggered conformation and the right side is the eclipse conformation. It is very hard to visualize the 3D structure. Therefore, a Newman projection is brought in to help you visualize the 3D structure in 2D fashion. This assumes that the viewer is looking along the longitudinal axis. For example, if the viewer is here, he will be looking at this end, and to the viewer, he would get something that would look like this. The left side is the staggered conformation, and the right side is the eclipse conformation. And you can get the staggered eclipse conformation from a staggered conformation if you rotate the carbon-carbon bond, if you rotate the sigma bond 60 degrees clockwise or counterclockwise. Let's look at the staggered conformation first. What you see here is the staggered conformation. As you can see, the hydrogens are maximum distance away from each other, which in return minimize the repulsion force. Therefore, this particular conformation is the most stable conformation. Compared to the other conformation called eclipse, so this is the ethane molecule in eclipse conformation, and if you look at it in the Newman projection view, you get something like this. And as you can see, the hydrogens are aligned with each other, providing a maximum repulsion force. Therefore, this particular conformation is the least stable. The major contribution to the energy difference between them is a stabilizing interaction between the carbon-hydrogen bonding orbital on one carbon and the carbon-hydrogen antibonding orbital on the other carbon. The electrons in the full bonding orbital move partially into the unoccupied antibonding orbital. The interaction is greatest in the staggered conformation because only in this conformation are the 2 orbitals parallel to each other. Such a delocalization of electrons by overlap of a bonding orbital with the empty orbital is called hyperconjugation. But let us look at the butane molecule. What you see here is the 3D version of butane molecule. But if you were to look at it in the Newman projection, so this is carbon 1, 2, 3, and 4. So if you look at the Newman projection for carbon 2 and 3, actually before we go into the Newman projection, let us substitute these 2 methyl group. So we have substituted the methyl group with red atoms. So these 2 atoms represents the methyl group. And let's look at the Newman projection between the carbon 2 and carbon 3. First, let's look at the different type of eclipse conformation. This particular eclipse conformation have methyl group aligned with each other and have 0 degrees between them. And therefore, this is the least stable conformation, and this have the maximum steric strain. The steric strain is the strain experienced by a molecule when atoms or groups are close to one another, causing their electron clouds to repel each other. But if you were to rotate this molecule 120 or 240 degrees, you will still get an eclipse conformation, but it will be more stable than 0 degrees eclipse conformation. So for example, if you were to rotate it, if you were to rotate this methyl group 120 degrees, so if you were to rotate like this, you would still get an eclipse conformation. And if you were to rotate it to 240 degrees, so from here you rotate it to 240 degrees, you would still get eclipse conformation. But however, this particular eclipse conformations are more stable than the 0 degrees conformation, because the methyl groups are pretty far apart compared to the other eclipse conformation where they are pretty close to each other. The other type is the staggered conformation. And there are different types of staggered conformation. One is the gauche conformation, which possesses 60 degrees difference between the methyl group. And you can have it rotated 320 degrees more, and actually 240 degrees more, and you will still get a gauche conformation. And this particular conformation is more stable than the previous ones. So right now you see a 60 degrees difference, but if you were to rotate it more, so this would be a 60 degrees, but if you were to rotate it 300 degrees, you still get a gauche conformation, and these two gauche conformations are more stable than the previous one. The other type of staggered conformation is called anti-conformation. So this is an anti-conformation, and it is a 180 degrees rotation between the methyl group. So the methyl groups were here before in the eclipse conformation, and you rotate 180 degrees and you would get an anti-conformation. This is the most stable conformation of all because you have the two methyl groups at maximum distance possible, and this have the minimum steric strain. What you see here is a methane molecule with substituted bromine, chlorine, and fluorine, and hydrogen. This particular methane molecule has an asymmetric center because it is attached to 4 different groups, and the configuration of this asymmetric center is R. To assign configuration, you need to assign priorities to each group, and the priorities are assigned based on their atomic number or atomic mass. In this case, bromine has the highest atomic number, therefore it is priority number 1, and then chlorine is number 2, fluorine is number 3, and hydrogen is number 4. The second rule is to make sure that the lowest priority group, in this case hydrogen, is pointing away from the viewer. After that, you go from priority number 1 to priority number 3, and whatever direction the arrow points is going to be your configuration. For example, in this case, your bromine is here and the fluorine is here, and if you were to go from priority number 1 to 3, the arrow is pointing in the counterclockwise direction, therefore this is an S configuration. But if we were to look at the mirror image of this, it will be an R configuration, because if you were to go from priority 1, 2 to 3, the arrow points in the clockwise direction, therefore this is an R configuration. But if we were to look at the Fischer projection of this initial molecule, actually before we look at the Fischer projection, let's define what the Fischer projection is. Fischer projection is a shortcut for showing 3D arrangements of group bonded to an asymmetric center. It represents an asymmetric center as the point of intersection of the two perpendicular lines. The horizontal represents the bonds that project out of the plane, and the vertical line represents the bond that extends back from the plane away from the viewer. So this is a Fischer projection of the initial molecule. And as you can see, this is priority number 1, this is 2, this is 3. So if you were to go from priority 1 to 3, you're going in a counterclockwise direction, therefore this is an S configuration. But if you look at the mirror image of this Fischer projection, it will be an R configuration, because if you were to go from priority 1 to 3, you're going in the clockwise direction, therefore this is an R configuration. But however, there are some times when you have the lowest priority groups being on the horizontal line, and in such cases you switch the results. So if you were to get S from going from priority 1 to 3, you switch it to R. But however, let's look at the butane molecule with substituted fluorine and bromine. So this is our 3D structure of a butane molecule with substituted fluorine and bromine. So if we were to do a Fisher projection for this, we need to make sure that the longest carbon chain is pointing away from you. So here we have the two methyl groups are pointing away from us, and fluorine and hydrogen and bromine and hydrogen are pointing towards us. So if we were to do a Fisher projection for this, it would look something like this. So we have our longest carbon chain being on the vertical line, and bromine and hydrogens on the horizontal, and hydrogen and fluorine on the vertical. So if we were to assign configuration, we go from priority 1 to priority number 3. So in this case, bromine has the highest priority number 1. So let's label this carbons 1, 2, 3, 4. So if you look at carbon 2, the bromine has the highest priority number, and secondly it's going to be this group because this carbon is attached to fluorine. So this is priority number 2, and this is priority number 3, and this is priority number 4. So if we were to go from priority 1 to priority 3, you're going in counterclockwise direction, but however the hydrogen is on the horizontal, therefore you reverse the configuration and you end up having an R configuration. And if you were to look at the carbon 3, you attach to fluorine, which has the highest priority, and then it's going to be this group having the second highest priority, and then it's going to be the methyl group having the third highest priority, and then hydrogen. So if we were to go from priority 1 to 3, you are going again in the counterclockwise direction, therefore this is an S configuration. However, the hydrogen is on the horizontal line, which is the lowest priority group, so you switch the configuration and you end up having an R configuration. So in S and R, in carbon 2 and 3, you would end up having an R configuration.